All right, let's dive right into a really cool chemical mystery. It's one of those things that seems super simple on the surface, but when you dig in, it actually gets to the very heart of how electricity and liquids, well, work together.
So, here's the big question. Why is it that some liquids can carry an electric current and others just can't? Why does salt water light up a bulb, but sugar water leaves it totally dark? Let's figure this out together. Okay, picture this. Classic science experiment. You've got 3 glasses of water. In one, you stir in some salt. In the next, a splash of vinegar. And in the last one, a spoonful of sugar. Then you take a light bulb rig and dip the wires into each one. What happens? Well, you get 3 totally different results. The salt water makes the bulb blaze bright. The vinegar? Just a faint, dim glow. And the sugar water? Absolutely nothing. Poof. Darkness. So what on earth is going on? Here is our first big clue. For any solution to conduct electricity, it needs one thing: charged particles that are free to move around. They're the little messengers that carry the current from one place to another. So it's not actually about the water itself, it's about what's swimming around in that water. But what are these mystery particles?
Let's meet the star of our show, the ion. Now, an ion is just an atom that's not neutral anymore. It's either lost an electron, which makes it positively charged, or it's grabbed an extra one, making it negatively charged. These are the freely moving, charged particles we've been looking for.
So, it turns out that substances that create these ions when you dissolve them in water have a special name. They are the prime suspects in our little light bulb mystery. Time to formally meet the electrolytes.
An electrolyte is pretty much any substance that, when you dissolve it, unleashes ions into the solution. It's the source of those charged particles that let electricity flow. It's really that simple. No ions, no electricity. A whole bunch of ions, a whole bunch of electricity.
Ah, but here's the twist. This is the key to the whole thing. Not all electrolytes are created equal, and that is why we saw such wildly different results with our 3 light bulbs. Even though salt, vinegar, and sugar all dissolve in water, the real difference, the thing that changes the brightness, is all about how many ions each one actually sets free.
So this lets us sort our suspects into 3 main groups. First, you have your strong electrolytes. These guys are super efficient, releasing ions almost 100% of the time. The result? High conductivity and a really bright light. Then you've got weak electrolytes. They only partially create ions, so you get low conductivity and, you guessed it, a dim light. And finally, the non-electrolytes. They dissolve, sure, but they produce 0 ions. None. Which, of course, leaves the light bulb completely off.
Okay, so we get it. Electrolytes make ions. But how? How do they actually do it? Well, it turns out there are 2 completely different ways a substance can generate ions when it hits the water. The first method is called dissociation. Now, the most important thing to remember here is that this is a physical change. The substance isn't actually reacting with the water, it's more like it's just being pulled apart by it. So think about it like this. Ionic compounds, like good old table salt, are already made of positive and negative ions. They're just all locked up together in a tight crystal structure. When you drop them in water, the water molecules just help those ions break free and spread out, letting them roam around. Let's call this the Great Escape. The water molecules, they're polar, right? So they act like a bunch of tiny little magnets. Their positive ends swarm the negative chloride ions, and their negative ends swarm the positive potassium ions. This attraction, this ion dipole force, gets so strong it literally pries the salt crystal apart, setting the ions free to carry a current through the water. Pretty cool, right? Now, let's talk about the second method, which is a whole different ballgame. This isn't about pulling existing ions apart. This is about creating brand new ions through an actual, full-blown chemical reaction with water. So take something like hydrogen chloride. It's a covalent molecule, not an ionic one, so it doesn't have any ions to begin with. But when it hits the water, it actually reacts with a water molecule and gives it a proton. Through this chemical transformation, it creates 2 brand new ions that didn't exist a second before, a positive hydronium ion and a negative chloride ion. It doesn't release ions, it makes them.
All right, we have all the pieces of the puzzle now. We know about strong electrolytes, weak ones, and non-electrolytes. And we know the 2 ways they can make ions. I think it's time we finally solved our light bulb mystery.
Let's put it all together. Salt is an ionic compound, a strong electrolyte, When you drop it in water, it dissociates almost completely, flooding the solution with ions and making that light bulb shine super bright. Vinegar, on the other hand, is a weak acid. It's a weak electrolyte. It only reacts a little bit with the water, creating just a few ions, just enough for a dim glow. And sugar? Sugar is a non-electrolyte. It dissolves, yes, but it doesn't dissociate and it doesn't react. It creates zero ions. No ions, no current, no light. Mystery solved.
So, if you're going to take one thing away from all this, it's this. Electrical conductivity in a solution is all about the number of free-moving ions. That's it. The more mobile ions you have swimming around, the better that solution is going to conduct electricity.
But hold on, here's one last little twist for you. What about perfectly pure water? Turns out even pure water conducts electricity. Just terribly. Why? Because only about 2 out of every 1 billion water molecules will spontaneously react with each other to form an ion. I mean, that is an incredibly tiny number.
And that leaves us with a really fascinating final thought to chew on. You and I were made mostly of water, and we're packed full of electrolytes like sodium and potassium. So if even pure water has this tiny, built-in ability to create charge, what does that tell us about the very nature of the electrical currents that power our nerves, our muscles, and even our thoughts? Pretty amazing when you think about it.